So here I'll be talking about k-uniform hypergraphs, which means that a hypergraph is a set of is a family of sets, but k-uniform means that all sets have the same size k. So we're talking about shortly k graphs. And typically, if I don't say it will have n vertices, and we often identify the hypergraph with the edge set. So sometimes we just say the size of the hypergraph would be the size of the edge set. And then there is one special hypergraph, the complete k-uniform hypergraph, where you take all possible k-tuples of the given vertex set. And the emphasis is on the matching. So here is a definition in picture. A definition of a matching is just a set of disjoint edges. And a matching is called perfect if its size is n over k. So it covers all vertices. And of course, a necessary condition is that the divisibility. Now, when we talk about hypergraphs, I will tell later about this Dirac result for graphs.
A matching just a set of disjoint edges?
Disjoint edges, just disjoint, yeah. Like disjoint, a family of disjoint sets. But perfect matching, you want to cover everything. Now, for hypergraphs, unlike for graphs, there is more than one notion of the degree. You may think of degrees of vertices, and that would be in sort of natural analogy with graphs. But you can also think of degrees of some sets of vertices. So here is a general definition where for a set of size d, we denote by dh of s the size. This is the degree, but of that set, and this is the size, is the number of the edges which contains that set. So, for example, it should be clear that you cannot have more than that many, but this is also possible. So this is not just linear in n. The degrees are now polynomial. Also, and then by delta d, we denote the minimum degree. The minimum degree over all sets of size d. So delta sub 1 would be just the minimum degree of a vertex. But you can consider other d, in particular, kind of interesting things that you can add here also the zeros, the empty set, because then the degree of the empty set is the number of edges. So you can have in one notation not only the degrees, but also the total number of edges. So here it is. And there's one observation which sometimes is used, that just by averaging, if the minimum degree, if the d minimum degree, delta sub d, is some fraction of what it could be in the complete setting, then the same fraction is guaranteed for the smaller d, for every smaller d. So it's just by averaging, and it is sometimes useful to deduce for free results from other results. So if you have something for the d, then you may have something for d minus 1. So maybe I just keep it for a while here and continue. And then actually, this line of research, which is mostly joint research with Vojta Rodl and Andrzej Rucinski, started with a similar but maybe harder question about Hamilton cycles. And it goes back to Dirac 1952, who proved, nowadays is maybe 2 lines proof, but at that time it was considered as a big result, that if the minimum degree of an n-vertex graph is at least half of the number of vertices, n over 2, then a Hamilton cycle is guaranteed. I hope I don't need to say what a Hamilton cycle is. And then, of course, there are many extensions, Ore type results, and so on, but I will just focus on Dirac and then jump to 1999, when Katona and Kierstead, and this is the younger Katona, the son, also Jula, but is the son, and Kierstead, they asked a similar question for hypergraphs, and they proved some bound, but basically what they conjectured that the minimum, now they look at this largest possible d in the definition of degree, so k minus 1 tuple. For a k minus 1 tuple, the degree is also linear in n. And they were hoping for getting an analogous result, so n over 2. They also wanted to have n over 2, and they got some counterexample which suggested that the actual precise threshold should be this number, n minus k plus 3 over 2 and the floor. Then you have a Hamilton cycle. And
what's the cycle?
okay, so here is another thing which you have many extensions. the notion of a Hamilton cycle can be defined in many ways. Actually, the first definition goes back to Berge, but I'm not talking about this one. They rather call it actually a chain, or now we call it a tight cycle, where you, by which you mean this picture, so that you can arrange the vertices cyclically so that every k consecutive vertices form an edge. So that's maybe the strongest, the most, also the nicest in a sense, due to its symmetry, notion of a Hamilton cycle in a hypergraph. But there may be many other, more loose or more even chaotic other definitions, but we're just talking about this one. And in fact, this is just a comment because I'm going to talk about matchings anyway. But that was a conjecture that it is, they prove something like a weaker bound. And then with Rodl and Semeredi, we proved this conjecture for 3 precisely and for all k asymptotically. And by asymptotically, I mean that we prove that for every k and every epsilon, from some n0 on, if this minimum degree of k minus 1 tuples is at least a half plus epsilon, then you have a Hamilton cycle. But it's still open here, for example, what about this, the other degrees, when d is less than k minus 1, say k minus 2 or less. In particular, for k equal, the smallest open case is then when you have just 3 uniform hypergraphs, so just triplets are the edges, and you look for the vertex degree, d equal to 1, and this is unknown. We got something with Rodl 11/12, but now I just met Andrzej Semeredi. He said he has a proof for the optimal number here in his head. So, it's optimal, it's 5 nines. But I don't have time to explain. There's a counterexample showing that you can do better than 5 nines. So we will probably need to work on Andrzej to tell us this proof. But let's go back to perfect matchings, which are my main topic today. So to make it sound more like part of extremal hypergraph theory, let's define this extremal parameter. So md of k and n is the minimum integer such that whenever you have a hypergraph on n vertices and with this minimum d degree, at least this m, then a perfect matching is guaranteed. Plus, of course, you have to assume divisibility. So it's always, if you talk about this parameter, the divisibility is built in. And it's for every d from including 0 to k minus 1. Now, of course, under this divisibility condition, Hamilton cycles, as defined, contain perfect matchings. You just take every kth edge, and you got a perfect matching. So, in particular, Dirac already implies that this parameter is equal to n/2. So this is just for graphs, k equal to 2, and minimum degree at least n half. Oh, I forgot to say that this Dirac is optimal in the sense that you can find graphs with just one less minimum degree, which don't contain perfect matchings or Hamilton cycles also. For this, we would need a perfect matching. So, but it's easy. And then another sort of easy case is m is d equal to 0. When you just talk about the number of edges, how many edges guarantee a perfect matching? So in a graph, in every k graph, for every k, what you do, you just isolate the vertex. So you take a click on the remaining vertices and minus vertices, and then this doesn't have a perfect matching because it says isolated vertex. But then if you just add one more edge, it can be proved. For graphs, is an exercise that you will always find a perfect matching. For hypergraphs, a little bit harder, and it requires some deeper result. So you need to know, say, that you can cover the entire hypergraph by that many disjoint perfect matching. So it's a factorization question. And Baranoy in 1973 proves that result. And having that result is trivial because this number is just the difference between the two. So if you look into the complement of this hypergraph, if a hypergraph has so many edges, the complement has not enough edges to block all those disjoint perfect matching. So one of them has to be present in the graph.
Do you need Baranoy? Maybe if you take a random perfect matching.
We didn't think long. We just found this that this is already a connection.
Normally for this you will not.
Probably we don't need the whole strength of it, but it follows anyway. Yeah. So from other existing results, so this case of d equal k minus 1 with Rodl and Semeredi, again, we proved for every k a precise result. So we actually found this parameter exactly. It is of this form, n over 2 minus k, and then there is some additional number, 1 of the 4, and you know exactly when is which. So it really depends on the divisibility. In fact, it depends, and you will see how it depends sort of from the lower bound construction. Here is a lower bound construction, which shows you that, in a sense, this number is best possible. So here is a construction. We practically split the graph evenly into halves, but we make sure that this top part has an odd number of vertices. You can always do that. I mean, plus, minus, you can, yeah. And this is why these numbers are not always the same. Depends on the parity of n, which of those is the case. Here I just proved a very rude bound. And then consider all edges, all k-tuples, which has an even intersection with A as edges. So these are all and only those are edges. Every k-tuple which intersects evenly. Then, of course, there is no perfect matching, because this is odd and you can only bite even at a time, so you never cover A. But then if you look at the degree, for example, if you take, if k is odd, then if you take k minus 1 vertices here, actually if you take k minus 1 vertices here, then the neighbors have to also be in B, because you cannot have just one vertex here and k minus 1 here. So this is the worst case. But anyway, this kind of bound we get. And then, of course, by this lower line over there, we immediately know also that this is also a counterexample for other d's, for all the smaller d's. So for all the smaller d's, we know that at least 1/2 is the right thing. And indeed, it was proved by Pikurko that our result asymptotically extends all the way down to half of k, roughly. So this is what he proved. And in fact, again, due to this line on the bottom, the relation between degrees, it was enough for him just to show that for this k over 2, that if you have this degree at least this much, you have a perfect matching. And then it follows from this and that for every bigger d. And the lower bound was already there. So, and in fact, he used some probabilistic method. That was not a hard proof. And then what was left was this case, which is still open. D between 1 and k strictly less than close is the lower half of D, except for 0, of course. And this is what recently there's a focus of many researchers trying to prove something about this case. So for the rest of my talk, I will be talking about this case. And one problem is that for this smaller d, you have another counterexample. Here is, I call it this fancy way, f, n, k, and but just look at what it is. It's another split of the vertices between A and B, but now A is smaller. It's just one smaller than the size of the perfect matching. And then as edges, you take everything which intersects A. So again, no hope for a perfect matching, because every edge intersects A, and A only has that many vertices. Not enough for n over k edges. But, and also, if you look at the degree, so another way to, and also more general way to give name to this graph is that you take a complete graph and remove a complete graph from here. And this would be S equal n over k minus 1, but for any S you can have this construction. And then the degree is, again, the lowest degree would be for a d tuple which sits entirely in B. And then it's exactly all minus which you cannot take, which is every extensions, k minus d extensions of the d tuple in here. So it's exactly this number, and asymptotically this is this number. It looks a little bit fancy, but if you say take k equals 3 and d equal 1, it is exactly 5/9, the one I mentioned about Hamilton cycles, because so far these thresholds for Hamilton cycles and perfect matchings actually go hand in hand. So it's like about the same. They are not exactly the same, but about asymptotically the same so far, all the known results. That's actually why we turned our interest. We couldn't solve these hard problems on Hamilton cycles. We started to look for matchings as a kind of training field for Hamilton cycles. But anyway, so this number is then, and then the question is which of the two. So we have two constructions, two lower bound. Maybe I put this one here now because. So we have two lower bounds, and sometimes one is bigger, sometimes the other. So in fact, the conjecture then is, and now everyone wants to prove that conjecture, is that this parameter is whatever is bigger of the two times this complete graph. So because the previous construction gave us 1/2 roughly, and this construction gives us this coefficient. So this is what people believe is true. And of course, it is consistent with Picurco result and our result area, because if D is at least 1/2 k over 2, the maximum is always 1/2 here. This number is bigger, which is not the case in the other direction. So there are cases where D is less than 1/2 of k, yet the maximum is still 1/2, like this one, 5, 2 and 5. It's 61 over here. Now there is some history to those problems. For this smaller d. This is for all, but of course we know it already for all the d at least a k over 2. We only want to know the smaller half of this range. But Dakin and Heckfis maybe were the first to consider this question back in 1981, and they proved this bound. So asymptotically, this is weaker than the bound here. Then Hahn, Persson, and Schacht did generalize it for arbitrary d. That was just for d equal to 1. This is for any d. Less than k over 2. Recently with Markström, first of all we removed a little bit from here as a cosmetic, but an improvement. He was especially happy to improve over the old result of Heckis, who was his supervisor. And then we also got some bound on the first unknown case at that time, which was M14. We got 42 over 64. Now this number here for 4 is 37 over 42. Over 64. 37 over 64, while we got down to 42, not enough. I mean, just this would give us 47 over 64, but we still pushed and got 42. But with not final success. And then the first success came from the same authors, Hahn, Persson, and Schacht I just mentioned, who proves this so k equal to 3 and d equal to 1. The first case asymptotically got 5 nines. And very recently, Keen, Osthus, and Treglon proved it precisely. So one thing is just to prove asymptotically, but one is to show that this is really exactly, that this counterexample is the one, and probably they also prove that it's the only one which gives you this. So basically, this number should be bigger by 1 than the counterexample, right?
This is for every n, not for large n.
That's I don't know exactly. It's probably no. They use all these asymptotic results also. So it's for large n. Everything here is for large n. Now, but they also proved more. They proved that in fact for every s, if you ask for the smallest vertex degree guaranteeing a matching of size s, because this was about perfect matching. But what about s? So the delta 1 threshold. So they proved that this similar construction with s instead of, or rather s minus 1 instead of this top. The top set should be of size s minus 1, and then you got a threshold for the largest matching, for the size of the largest matching. So they got this general bound. And this is interesting because this is like a continuous thing. So in a sense, it goes down along the same formula with S. So for perfect matching, you plug in S equal n over 3, and then you go n over 3 minus 1, and so on, and you got a whole range of thresholds which move according to the formula. And this is not the case when you consider other degree. I mean, in this case, it's just one other degree, delta 2. If you consider delta 2, then there's a jump. the threshold for every s smaller than n over s is roughly s. I'm now talking about delta 2 degrees, so degree of a pair. While for perfect matching is, as I just showed, n over 2. So it's this jump between n over 2 and n over 3, just going from perfect to almost perfect, to just without one edge. That's already an interesting thing. Same for every other k when you look at this highest degree, k minus 1 degree. And the techniques used so far in all these results were based on the absorbing technique introduced in one of our papers. Can I take this off somehow? My pullover. Yeah, so this absorbing technique is based on a kind of trivial observations that if you want to include a set of vertices of size k, s, to a matching, all you need to do is to replace certain number of edges of that matching with a set of just by one more number of edges, which includes that set. So here is an example. If this is a matching M and this is a set of k vertices which are not covered, all you need to do is to find these two edges. If there are, you can replace this green edge with the two red edges, and you are better off.
You should show it because this is covered.
Oh, it's covered. Okay, yeah, thank you. Actually, I want to show you the next one separately. That's why I covered. So once again, if this is a set of vertices outside the matching, this is an edge of a matching, and you are happy to, you are just lucky to get these two edges, you can extend, right? And the problem is that such things may not exist for every k-tuple. So for this one to exist, you would need to know that the degree of every 3-tuple in my picture would be more than a half of n, because at some point when you construct these 4 vertices, so these are given, and you want to construct these, you take one in say, whatever is the degree of this triple, but then when you get down to this vertex, you want to choose a vertex which is at the same time a neighbor of two 3-tuples of vertices. And for this, you need more than a half. Then they intersect. Then there is some. Here is a more clever construction, which due to Han, Persson, and Schacht, which allows to do the same thing under these conditions that only the vertex degrees are large. So if you know that the vertex degrees are large, then so here are these 4 vertices which are outside, and this is a matching. So if you replace the 3 green edges by the 4 red edges, you include those, you absorb the vertices into a matching. But the thing is that for any given 4 vertices like this, it's easy to construct this green part, because, for example, here you would need to find 3 vertices which are common neighbors of 2 given vertices. And again, because the delta 1 degree is more than a half, you find such triplets which are common. We are even more, it was 5 nines, but so they were kind of comfortable. But there are many other constructions like this which are used in those proofs. And then, yeah, but what we do, we flip a coin and select a very few of those which serve all k-tuples. So here is actually an outline of the proof. Of all these proofs so far, I mean, like our proof with Semeredi and Schacht in his paper with students. So there are 3 steps. So maybe I shouldn't cover. Like it just goes like 1, 2, 3, right? In step 1, we find a small matching, absorbing matching, MA, so that every k-tuple finds some S-absorbing device in it, like I just showed, of some kind. So that in the end, if you are left with k vertices, they can be absorbed. And now the second step, so we put this matching aside and find a large matching in the remaining hypergraph. Now large means almost perfect, leaving just k vertices, but in some more recent proofs, it would be even more than that, but then you would do repeatedly this absorption in many rounds. But suppose we just leave k vertices out, so then we absorb them and we got the perfect matching. So that's like a main idea of all these proofs. Unfortunately, to prove anything about other cases, it tends to be so hard that, as I said, this is still open. This is a case when k is less than d over 2. And with Rodl, we thought about the following approach, an approach which uses fractional perfect matchings. So here is a definition of the fractional perfect matching. So instead of just taking an edge or not to a matching, we just take an edge partially or fractionally. So we just assign weights to edges, and then the only consideration is that if you take a vertex for a perfect match, for a perfect fractional matching, a vertex should be included into a set of edges which sum up to the weights sum up to 1. So this is then a fractional version, and in fact it justifies the reasons that then the total. Oh, I forgot to put the W of E, but the total weight is then exactly n over k. So it's like it should be. And in particular, if you take just zeros and ones as your weights, you are back in the integer version of it. And we then thought that maybe we should use Farkas Lemma, which exhibits the duality of those problems. So what is Farkas Lemma is this one version of it, that if you have a solution to this system of equations, then you don't have a solution to this system of inequalities. In fact, I'm going to use it in the opposite. So if you don't have solutions here, you have solutions here, but it's the same. Now, how we apply it, or we take the incidency matrix of the hypergraph. So you have a hypergraph. You can think of a matrix which has columns assigned to the edges, and vertices are the rows, or rows are the edges, and vertices are the columns. And you put a 1 if the vertex belongs to that edge. And then with B being just a 1, 1, 1, 1, this thing corresponds to having a perfect matching. This is exactly having a perfect matching, because you want for every vertex, if you sum over all edges, you want 1. And of course, it's not have to be non-negative. But I just want to do it in the reverse. So now I want to emphasize that if you have no perfect matching, then this then there exists. So then you have a solution to this system, which means that you can find a weight function over the vertices of the hypergraph, so that for every edge it sums up to a non-negative number, but the total is negative. Total negative corresponds to this. For every edge, non-negative corresponds to this. So once again, so not having a fractional perfect matching is equivalent to saying that there is a weight function on the vertices, so that every edge has a non-negative total, but the total is negative. And so similarly as before, we can define this parameter, external parameter is exactly the same. So this is the smallest, given a d, k, and n, this is the smallest integer, so that if you have a hypergraph with n vertices, it's a k-uniform hypergraph with n vertices, the minimum d degree is at least m, then you have a fractional perfect matching. So this is a new definition, but it's very similar to the previous. The only difference in these two places. And again, if you look at this construction, it provides also a lower bound on this parameter. In fact, and the best. So here so I call this graph just f. The only thing is that you have to put because now n over k does not need to be an integer. We need to put the ceiling. And then if you just assign k minus 1 to all the vertices in A and minus 1 to all the vertices in B, these two conditions, which as I said, are satisfied. So there is a weight. This is a weight function which exhibits this as a part of Farkas Lemma. So there is no fractional perfect matching. Why? Because every edge, if every vertex in A has a weight k minus 1, then every edge is safe. Every edge is non-negative, because every single edge is just negative 1. But the total, if you just sum up, because you have only n over k minus 1, then the total is negative. Now, of course, there are some observations. So first of all, this fractional parameter is not bigger than the integer parameter. Sometimes they are way apart. Like it was easy. We already know this parameter is just this number, n over k roughly, while for integer is around n over 2. So they're way apart. But for other instances, they're equal. So we were just curious what's going on here and whether we could use this fractional approach to get down this real thing which we are after, namely this this M without the star to solve the problem for matchings. And indeed, we thought we are optimistic at some point, because here is, I'm just recalling the conjecture we are after. I already showed you this one. It's just, again, for your convenience. And now here is a new conjecture. It is, let's say, weaker conjecture, which specifies the size asymptotically at least, or in the exact form. It would be, of course, stronger than this one. That the threshold for the Dirac type threshold for the fractional perfect matching is always this part of this among those two. So for some D, for D in the upper half of this range, this number is smaller. So it's maybe not so useful for us. We already know everything. But for D smaller, in most cases, this is the one. But anyway, the following theorem shows that they are strongly related, as then in fact solving or estimating the fractional parameter would yield the true one, the integer one, because so this one is always the bigger of the two. So either it is 1/2, roughly asymptotically 1/2 of the maximum degree, or it is asymptotically equal to the fractional. And this theorem is not hard. Probably I will not have time to.
Just to see, so conjecture 2, so there is a difference between M star and M in all the upper range.
In the upper range.
There is a difference between M star and M.
Yeah, M is in the upper end. We know that M is always 1/2.
It's half, right?
A half of yeah.
Because the first example doesn't do anything for fractional.
Exactly. The first counterexample is based on parity, so it cannot do anything for fractional. This one is based on size, so that's why. So, and this is what I just said, the theorem 1 and conjecture 2 star both imply conjecture 2. So, and the theorem 1 wasn't very hard to prove. Certainly, it could be proved using regularity lemma for hypergraphs, but we tried to avoid it. So we came up with a proof which just uses coins, flipping coins. How much time I have still? Maybe I can.
Yeah, you have time.
So I can go over that proof, maybe an outline. Yeah. So that proof is based on 2 results already. So in a sense, we are in a good position because we can use these deeper results. So there is an old result of Frankel and Rodl. It says that if in a hypergraph, and here actually there are no restrictions on the uniformity of that hypergraph, but if all the degrees of vertices, all vertex degrees are about the same, some number d, which has to be large but not that large, and then so all degrees are roughly the same, and then all pair degrees, this is like the little delta 2, but now the capital delta means the maximum. So every pair of vertices sits in little of the. They were more specific. These conditions are more specific. I didn't want to overwhelm you with the details of some logarithms. But roughly, this is what it says. That if you have a hypergraph which is so nice, that it's like almost regular for vertices, and then pairs, there are no pair which appears in too many edges compared with the degree. So then you have a matching which is almost perfect matching. Almost means 1 minus epsilon fraction of the vertices can be covered. And then there is the second lemma, which is actually a version of the absorption technique, which we took from that paper, that if the d delta is more than a half, significantly more than a half, then there is a matching which is very small, little o of n, and such that for every set of not too big set of vertices divisible by k, you can add it to that matching. In a sense, that you can find another matching which is bigger, it's just on the same vertex set plus the w. So it's like the absorption, but now on a bigger scale. You have little o of n vertices to be covered, and you can do it. And in fact, the proof of this one is using those constructions I showed you, and they do it one by one. But anyway, this is nice because then all you need to do is to find an almost perfect matching. Once you have an almost perfect matching, in view of lemma 2, you can extend it to a perfect matching for free. And this tells you when to find an almost perfect matching. So they really work together very nicely, these two results. And all we have to do is now take a hypergraph, an arbitrary k uniform hypergraph, about which we only know that the minimum delta d degree is large, as appropriately large. And we need to show, of course, it doesn't need to be like this, but we are going to find a sub-hypergraph inside that hypergraph, which is like this, by flipping a coin. That's the idea. Okay? Second lemma says that if I find an almost perfect matching, I mean, no.
M2 is a complement.
M2 is very small, but it means that if I have this M2, I put it aside, find an almost perfect matching in the remaining hypergraph, and the remaining still has a large degree because I just put aside very small.
Okay.
So then I find an almost perfect matching.
W is what's not covered by the.
Yeah, this is what it would be missing from perfectness. But this of course, this little o has to be different than this. I mean, there must be some relation between these two little o of n. This must be bigger than this. Otherwise, you couldn't swallow everything. But then using this M2, you swallow everything which was not covered by.
So M2 will be part of the almost perfect matching.
You could, yeah, sure you would add it. Because you put it aside. So yes, of course, it will be disjoint. So anyway, it really boils down to verify this. So to find a sub-hypergraph which satisfies this, and I don't know if I should go. It's impossible probably to comprehend it the details, but at least the idea. So we start with something which is bigger than both, and then here actually are the 4 steps. So I can still tell you this. We find this the absorbing matching. Still, we have a large degree because it was so small. Then we have to find, and this is where we are using coins. We have to find this sub-hypergraph, spanning sub-hypergraph, same vertex set, which satisfies the lemma 1 with, say, d.
You report that you can talk until 12:15, right? So,
Okay, yeah. I know, but still I have something else to say. Yeah, it's surprisingly fast compared to the blackboard I used last time. Okay. Maybe you should interrupt me more. Okay. So the 4 steps once again. We find this magical matching, put it aside, find a spanning sub-hypergraph of the rest, which satisfies the assumptions of this Frankel-Rodl lemma with some d. Then by that Frankel-Rodl lemma, find an almost perfect matching.
this is what, so using the fact that the minimum degree is big, you can find something that is more or less.
Yeah. So this condition is needed, first of all, to apply this absorbing lemma. So we need 1/2, more than 1/2, and now that we are above m star, we are really using it in this random approach. Because maybe I'll show you if I have time, and then we just. Yeah, and then we just put 2 things together, and there is this W missing, but we can absorb it using this absorbing lemma, this other matching, and everything then is perfect. So this point 2 requires some explanation only, how to find such a almost regular sub-hypergraph inside a given hypergraph. And here is, so this is about this step 2. So what we do, we flip a coin, and this is a coin, p equal to n minus, of course, all these numbers could be probably changed, with a small probability coin over each vertex. And we do it not just once, not just once for every vertex, but we do it n to the power 1.1 times. So we have that many rounds, and in every round, we flip a coin over every vertex. We select a subset of vertices. We select so many subsets of vertices, right? R1, R2, R to the index n to the 1.1. So we got lots and lots of induced sub-hypergraphs on these selected randomly sets of vertices. And then we have all these properties of them. They all behave predictably using Chernow, using Jansson. And maybe the most important property is the fact that every edge, if selected entirely, is only selected by one of those sets. This is in at most one of those sets. This is why this number set to be so small. So every edge of the original hypergraph was selected only, it's its own entity at most once. Only in one of these induced subhypergraphs it sits. And then we also know, because the degree was large to start with, it's also large. Here is a mistake. I should say M star D, but with this number of vertices of the Ri. So it's scaled down to this small subhypergraph. And then we are using the fact that, so now we take the union of those, but each of those separately has a fractional perfect matching, and we use those fractional perfect matchings as our second round of coins. So for every edge, we flip a coin, and this is like the second round of randomization. First, we selected only vertices many times. Now we select edges using the fractional weights as probabilities. And this way, we obtain what we wanted. And here is a quick check. I don't know if you can, maybe just the first part. So just the expectation. So what is the expectation of the degree of a vertex then? Oh, we sum over all edges selected, and this is the probability. Selected in the first round, and then the probability. Mm-hmm. Yeah, I first just chose vertices many times, so I got many induced subgraphs. But every edge is in at most one of them. If it was at all contained, it's just in one of them. And each one of them has a fractional perfect matching. I call it Wi. So then, and there is this unique index, the IE for every edge. If an edge is there, it sits in only one. And then I'm using this weight for the probability. Now I'm flipping coins over edges.
So what would have happened if you would have flipped coins to begin with over edges according to the fractional matching in the visa, right?
This wouldn't be enough, because then you'd only got one edge. Every vertex would be only in one. If you think about it,
do it many times.
You would need, this is exactly what we are doing. If you just apply the fact that there is a fractional perfect matching, and every edge has its own, but then if you just jump and apply this immediately, you would get a subhypergraph where every vertex has degree 1 on average.
And then you do it again?
No, this is what we don't do, right? We don't do it. We do it this way. We first go over the...
But what would have been wrong if you do it with the original fraction?
Because it would be too small. We want to find a matching, hypergraph.
I will do it many times. It takes a union of everything that I get.
So maybe it's equivalent to what we are doing. I don't see it yet.
I'm kind of wondering why do you restrict to the sets of vertices? Well, maybe,
I don't know. It's just that this way we knew that every edge is in at most one of them, and we had for each one of them a fractional perfect matching, and so we had like a set of coins for each. So we split the edge set into disjoint, and each one of them had a fractional perfect matching. That was it. Sorry?
What will capital D be?
What's the?
The capital D that you're going to get for the point.
Yeah, so n to the power 0.2. Yeah. So here actually it comes out. So if I take the vertex and now look at all the edges which were selected in the first round by selecting vertices, I selected some edges, not all. This was this H star, and now this H double prime is a random subset of this H star. So I sum over all, but I can split it accordingly to which set Ri was that edge in, and now these are just ones, because by the definition of fractional perfect matching, and the size of Ri, I mean the number of let's see what is 0. Oh, I had this property that for every vertex, the first property here, for every vertex around n to the power 0.2 sets contains that vertex. That was trivial, and so I'm now using this fact. So this sum has that many elements, and each of them is equal to 1. So, as I said, there are other approaches. Some people say it can be done by regularity. I wonder if it would be simpler or not, but we like that proof. especially Vojta Rodl likes that proof because it refers to his own result with Frankel. But now, so in my last 10 minutes, let me show you our unsuccessful attempt to prove this conjecture 2 star, which, let me recall, was just to show that the fractional parameter was equal. Yeah, I have it here, so maybe I can put it. So to this conjecture 2 star, which would actually give us the main conjecture 2. So we try this fractional approach. So we want to show really this. We want to show that if there is no fractional perfect matching, then the degree of a hypergraph, the d degree of a hypergraph, cannot exceed the degree of this counterexample, which I just put away from this projector. But that was the one which gave us the lower bound, and we now want to show that it's really also an upper bound. And by Farkas Lemma, it really is enough. So we have this inequality that if there is no fractional perfect matching, then there is this weighting of the vertices so that the total is negative, but for every edge, the sum is non-negative. And now, just to, actually what I'm going to show you is just a sequence of steps which are sort of equivalent and leading to another problem which we cannot solve, but still maybe something is an interesting connection. So first of all, we define for every C, but we only need it for C equal to 0 and to 1, we define the threshold hypergraph given a K, given the weight function and given a vertex set. We define by this a hypergraph which consists of all K tuples which sum up to at least C. So I have a weight function on every vertex, and now I select as edges only those K tuples which sum up to the total is at least C. So here we are talking about C equal to 0. So in particular, this H for which such a weight exists is always contained in this, because this is like a maximal. If you have such a weight function, maybe some edges, I mean every edge sums up to at least 0, but maybe there are some K tuples which are not edges, yet they still sum up to at least 0. But so we would add them here. So this would be so in fact, because of this, we can restrict our what we want to prove only to this kind of hypergraph, threshold hypergraphs. So it suffices to prove that, in fact, for every, now we don't even have a hypergraph to start with. We have just a weight function which assigns real numbers to vertices, to this set of vertices. There are no edges yet. Total has to be less than 0. And we define this hypergraph where we include as edges everything which sums up to at least 0. And we want to show that the d degree of that hypergraph is not too big. That would make us happy. Now, without loss of generality, we can assume that the smallest weight is -1, just by dividing. The 0 condition doesn't change if you divide. So we can have, and then of course, if the smallest is -1, we can assume that the largest is not bigger than k minus 1, because then again, every vertex with more than z is already complete. It has all its degrees complete. So we can restrict to this. Moreover, and this requires some argument which I will skip now, we can assume that the d lowest weights are equal, and therefore equal to -1. Because if they are not, we would replace them with an average, and still had a hypergraph with the same minimum d degree. So this requires some thought, but let's believe me. So we have not only this range, but also that this lower bound is achieved by at least d vertices. The d lowest are all -1. Then we still shift it a bit because I don't like this range -1 k. Let's make it 0, 1, right? So we just add 1 and divide by k, and we are in the 0, 1 range as we like to be. It's just for simplicity, nothing else. Yeah, there's some wind here. Okay, so now after this substitution, finally, it is equivalent to prove this. To prove that, maybe I put it up, for every weight function which assigns between 0 and 1, And the total now, instead of 0, is n over k, because I added 1 n times and then divided by k. So it's n over k. And at least d vertices got the weight 0. We have this inequality. But now I replace 0 by 1. The threshold is now 1 because I changed it. I added 1. So it was k, and then divided by k. So it's 1.
This is like the usual notion of a fractional cover.
Yeah, so this is now, yeah, we are getting to it. But one more step we have to make, namely, this is about the degrees, the minimum degree of a D tuple. Now, in this graph, I can actually take the smallest, the D vertices with the smallest weights, and look at the so-called link or neighborhood, and then just count edges in the neighborhood. And this way, we make one extra step, and we reduce our problem to the problem of a two-run type problem, just how many edges you need to guarantee a perfect matching instead of degree, right? Because if you fix a D tuple, you know it has the smallest degree, and in these threshold graphs, the smallest, the D vertices with the smallest weight, in this case, all of them have just weight 0, then the minimum degree would be equal to the number of edges in their neighborhood, the edges of size k minus D. So this is my next slide, which shows you this operation. Explain it again, maybe. It fell down. So here is actually the explanation of this step once again. So for both sides of this, remember, I want to show that this is not more than that. That this is the number, the degree in this threshold hypergraph is not bigger than in this construction. But both of them can be now turned into just counting edges of size k minus D in the corresponding neighborhood. So here is this set S on both, and here's an arbitrary threshold hypergraph, and I'm just counting extensions. Because they sum up to 0, I'm still counting those which sum up to 1, at least 1. So this is still 1 here. Now here, I am just, I'm looking, I take the one which is any set of size S here, of size D, and then I'm counting how many k minus D extensions intersect, because they have to intersect in this construction. So it really boils down to the following lemma to be proved. I mean, it's a lemma, this is a conjecture at the moment, so we don't know how to prove it, at least in general. So now I switch from k and n to L and M, because now we are talking about, in fact, maybe I add this line. So L is now k minus D, and M is now n minus D, because we change these numbers. But otherwise, it's, so for every L, at least 1, and for every M, big enough, for every weight function, which assigns weights to a set of size M, weights from interval 0 to 1. And in addition, the total weight is not bigger than M plus D over L plus D, because it used to be N over D, N over K, and now it's this. We have that this hypergraph cannot exceed in size this magical construction.
So what do you know? You probably have some upper bound. What do you have best upper bound?
Yeah, but we are really not satisfied with upper bounds. We could, yeah, instead of the size of this is also, we know it, is this 1 minus 1 minus 1 over k and so on. So for example, we can have it 1 minus 1 over k, which is like what Dekin and Heckfis proved. So this is easy. We can also prove it here. But now what we know is that this lemma is true for 1 and 2. It includes 1, yeah, now, singleton. So it's a funny hypergraph, one uniform hypergraph. And here is actually a proof for that. It's a one-line proof. But it kind of provides a nice proof of something which, if you didn't switch to the vertices, it wouldn't be so trivial. And for 2, it's also easy, and it also follows from the fact that because this can be viewed as I will talk about it in my last slide, if I can still. This is like a vertex cover, and for graphs, it only assumes optima at 1 and 1/2. So this helps, and that's an easy. There is such a result that these problems are. Yeah. Okay. Yeah. So I have just 2 more slides, and which connect to this. Okay. So now this assumption, as I said, this assumption that the total is less than something can be translated into the modern language to say that this is like the fractional vertex cover is less than this, which is same as vertex cover, but so and then by the duality theorem we can go back to fractional matchings by saying that this is equivalent then to say that the fractional the size of the largest fractional matching, not perfect, but largest fractional matching is less than that. Here is the explanation. So once again, this condition, which appears as an assumption in our lemma, maybe I still put this lemma here. Can be viewed as a bound on the smallest fractional vertex cover, and by duality they are equal. So there are dual problems. So therefore, this also is less, and this is defined here as a linear programming problem. Maximize this, the sum of the weights, knowing that for every vertex you don't exceed 1 if you count all the weights of the edges which contain it. It's called maximum fractional. So what we really need is now that for every L graph on M vertices, we just want this inequality, that if the fractional matching is smaller than, the largest fractional matching is smaller than this quantity, this fraction, then the hypergraph does not exceed the size of that hypergraph which we had there, which is this. And more generally, we can ask, because for our purposes, we just need this special value, but you can ask more generally, what is the threshold for the fractional matching to be at least S or be less than S in terms of edges? Now we now forget about degrees. We're talking about just edges, and we had to add. So this is the thing which is exactly here, but we had to add this extra term, maximum of the two, because for the very large values of S, this hypergraph takes over. It's a better counterexample because this is a complete graph on this many vertices plus some number of isolated vertices. So this is the number of edges, L edges. This is the size, but it's better. And there is somewhere this transition point, which is fortunately above this, so we don't worry about it so much for our application. And now I call this conjecture, and still I believe it's open, conjecture 3 star, because there has to be an integer conjecture like this, not fractional, but the integer counterpart. And indeed, we found it. We found that such a conjecture exists. And in fact, for long ago already, it was stated by Andrzej in 65. So here is the conjecture. It looks exactly the same, except that we don't have the stars. So it says that if you have a hypergraph, L unified hypergraph without a matching of size S, so the largest matching is at most S minus 1, then it cannot have too many edges. And again, 2 cases. Now, this is only true for the graphs, and that was even proved earlier by Andrzej and Galay, probably using that theorem. But there is a more modern proof by Frankel using switching technique. Shifting technique. Maybe Noga, you know what shifting means. And then for other L, for real hypergraphs, is only proved for very small s, very small, like not enough for us anyway. Too small s. For example, Bolobash-Dakin and Andrzej. And recently we learned from Frankel that he is still working on this problem, and he can prove it for S at least not bigger than m over 4.7.
So for S equals 2, this is Andrzej-Corrado, right?
For S equal 2 is Andrzej-Corrado, but S equal 2 is at the other end. We are not, yeah, but that's true. It's just non-intersecting. If you don't have a matching of size 2, it means that your family is intersecting, right? So it's Andrzej-Corrado. So it is strong, it's more general than Andrzej-Corrado. So Frankel is still working, and he got this, m over 4.7. If you got 4, you would be happy, but in general, this is the number we need for L equal to 3, this is the number, and at least this gives us something, because we would be otherwise very frustrated having such a approach. For us, it seems to be very nice to go through fractional and then end up with something very hard. So because of this, we for example know that our conjecture to star, the fractional conjecture, is true. We don't have it for all these all the cases when the difference is 3, but beginning with d at least 2, not 1, 4, but say 2, 5, and so on. And in particular, among those cases, there's only one case which was not covered by this conjecture 2, when d is less than k over 2, namely 2 and 5. So we got one new result, that this parameter m2 of 5 and n is indeed, that was the case, remember, 61 over 125. So this is the case when 1/2 still beats the other number. So we got this is our only new result. To get this one, we would need Frankel to improve it to basically m over 4. We would need this. But I just learned, unfortunately I don't have a pen to write the name, that a student of Andrzej Rucinski just proved, computed this number precisely. And his name is Kahn, but not like Jeff Kahn, but it's Khan. Khan. He's a student who is soon to graduate, and he also got 3, but that was the same as Keen Osthus. But recently, I just learned it over the weekend that he got this number not only asymptotically, but not only 37 over 64, but precisely that construction. So thank you very much. I think I went over.